Bájale un poquitico el volumen, un poquitico solamente.
Hey.
Hey, Andy.
Sorry, I'm late.
No problem.
How's your day been?
Better. Better than last week.
What makes it better?
A more organized workflow for this week has been immersed in some continuous meeting, but at least this week I have had some time to work in some specific planning that I needed. Otherwise, I will become crazy. It's too much work for a single person.
Yeah.
And also,
yeah, I totally can feel you there. Regarding this is too much work.
I have some news for you. Do you remember one of the two guys that were under the media?
Yes.
They both recover. They are above the 60%. And
Very good.
one of them, he called me yesterday because the issue that I pinged you by Signal.
Yes.
I was able to fix. It was a nonsense. It was just 2 lines of extra code that was supposed not to be there. So he was able to fix it, but he completed the project, and he told me that he will to enter the office hours from time to time. So he's willing to improve his average. So it's a good news, at least to me, is to see that
That's
somebody.
very good.
Sorry, say again?
That's very good.
Yes, yes.
But why were these? Why? So they were never in recitation. Why is that?
No, but I assuming that maybe is a conflict with the work schedule. I will ask him during the next office hour this Friday to see why.
Yeah. How did
Chances are
they?
that maybe today he attends. I don't know.
Yeah. How did the office hour go on Friday?
No, not well. No, this time attended only two people, Rodrigo and Marta.
Classic.
They were just absorbed with the project completion, so not much relevant query or question that they have. So
Yeah.
the rest, I assuming that they were hitting to finish the project. So
Yeah. Before we go, I just want to talk you through what's going to happen today, so that you can also tell me. So I'm going to take some time to go through what we did last week, because I was confused. So I think it's good. I will essentially go through the note with everyone and just show them this again.
okay.
Then we have some warm-up exercise on the Jamboards, which is you label some neural net.
Okay, 2 layers.
So 2 layers, but like right where these belong, and there we'll present slides. Then there's also the second part, which is activation functions, where they should find the derivative of different activation functions.
This is good because this give a graphical view of how the functions behave. So it's really good.
And then we do a lot of derivatives, where I will start with the first and then send them off into more. Hey, Ricardo.
You have a message here.
Okay, Ricardo is. And then there is a coding exercise on a variant of SGD, which is, so here they will minimize one function with SGD, which seems to look a bit suboptimal. And if you do something else, then you're much straighter. And the idea is to change the update a bit.
Okay.
This is where so what you do is you not completely take the learning rate, but you take also the last update into account a bit. And yeah, there we have, so the code I also sent. Yeah, did you hear any things that learners are particularly would like to have focus on?
No, not at this time. I commented, I believe I did during the last,
Yeah, this last
the,
was shit.
that, no, 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 I commented then in the message that I sent, your message, I added some few extra words. I mentioned that we were going to go through neural networks in the next recitation, and
Yes.
this topic was a bit more funny and
Mm,
interesting than
totally. Yeah, yeah, yeah.
any previous.
Yes, totally. Ricardo, are you here? Actually,
Yeah,
maybe.
I entered it before. Sorry, I'm
That's all
just.
good. That's all good. It's good to have you. We are just still talking talking about stuff. If you want, you can already download the materials
Yeah,
from the
yeah.
shared note.
Okay, I'll be doing that.
Then let me open a bit of the code. Are you outside, Ricardo?
What, excuse me?
Are you outside, Ricardo?
Yeah, I'm outside. Yeah, I put the camera, but it's not working.
Well, that's so nice that you're outside. And Hugo, in which way do you get less work? So how do you?
Sorry, say again.
So like you were saying, it's too much work, and how are you going to reduce your workload?
You know, I'm a skill in analytics.
Yes.
So besides the PM artifact that I supposed to use, I always had a good, a massive doses of analytics reporting. So,
Yeah.
for example, I'm able at this time to look in a single pane of view at 4 different projects at the same time. All are related to the same program. But if you don't do so, you will. I should be. I'm doomed to go over Azure DevOps, review one project, then go to the other project and review what's going on. But I lose the synergy amongst all those projects because in most cases the resources I have to accomplish a given task are
Yes.
common or are shared with all these projects. So if I am unable to put into a single BI report, it's easy to determine ever some overlapping or some over allocation of resources.
Yes.
So
Yeah.
it's great. And also handling large volume of data. Since there are some restrictions, I'm skillful also in using some database system like
Yeah.
SQL Server, MySQL, but
Yeah.
it's restricted in the company. I could request access, but it's restricted. So I found an easier way to combine or analyze data, just importing different source into a Power BI report and establish the relation amongst the different tables and filter out quickly. The queries are really fast and easy to implement. So that reduces a lot the amount of manual work that any PM should regularly be doing. But everybody's convinced
Sorry,
yet that
PM is project manager.
yes, I work like a project manager at this time.
Okay. Hey, Juan. Is it actually Juan Manuel or Juan is better?
You're in mute, Juan.
Hey. You're still working. Okay, that's good. I have still the camera on.
This job nowadays is much simpler than some others I have had in the past. And at least I'm working almost completely to the project manager and the academic area. So no other disturbance. But in the past, I used to work like IT manager, like also teaching some like corporate instructor, and also like a pilot. So it was really a mess. I can be here, finish the class, and maybe fly to the other part of the work, and have to be back before the next Monday, so the next morning. So it was.
Sorry,
really,
you were a pilot, Hugo.
Yeah.
That is so cool.
Yeah, it is. And really, that's one of my favorite experience in life. Flying is amazing, especially depending on the kind of aircraft you fly. That makes the difference. But
that is okay. And what kind of aircraft did you fly?
none that you have ever heard or seen before. I can assure you that is a totally restricted type of aircraft. Have you ever heard?
That sounds very confidential.
Well, I have enough authorization level to some disclosure, to allow some disclosure. So, and most of the time, people not even believe what I'm saying. So it's okay. It's hard to it's hard to assimilate. For example, do you know about VSTOL aircraft? Vertical short takeoff, a Harrier,
Are these like the ones that? Are these like the ones that you start from like a ship? Like from a military, like how is that called? But you have like these that almost
yes,
they do like this.
Exactly.
Yeah.
Okay. There is even a more advanced generation of that kind of aircraft. It's called AVSTOL. VSTOL stands for vertical short takeoff and landing. So it's literally Harrier. You can take off vertically and land that way. But the A stands for amphibious. So it can go
my gosh.
on air or below below water. So it's an amazing experience. It's like, I don't know, piloting a starship or something similar. It's really cool. But it's not anymore. I'm somehow retired, so I'm not doing.
And why did you retire?
Why? I retired twice. When I get married, and then I continue in the background, and then more recently because Uruguay is not properly a good basement for this kind of operation. So is
But this means you were a soldier. Or
well, special forces technically, but not exactly a soldier. But yeah, it's a kind of special forces.
okay. That's amazing. That's so interesting.
Yeah.
I don't know. I'm in Germany the first year I was the first cohort of students, high school students that didn't have to go to the military, and I was this purported math genius in school, and I regret very hard. I think I would have benefited a lot from either working or going to the military for a year.
So you didn't went to the military
I didn't go.
service?
No, I didn't go.
It's okay,
It's a bit of a, yeah, it's a bit of a pity, especially in my, that's now, yeah, we're like not so many people, but especially in the group that I grew up in, like in a very left family, I'm much more pro Germany needs a military still in these times than most others. And yeah, I think that's very important work.
I did train for some months in Germany.
Hey, Victoria.
Hello, how are you?
Hi, Victoria.
I'm coping. You look a bit tired.
I'm almost dead.
You're almost dead.
Yeah.
But does that mean you're going to die soon? That would be bad. I hope you can make another 2 hours.
Okay. Yeah. I hope
No,
so.
then it's like I feel that's bad if you don't die during a recitation.
No, I think that
After
will be
maybe, after maybe, but not.
I'm
no.
drinking mate, so
All good. Okay, I need like 2 minutes, so I'm going to be back. And we start as always at 35. That's like the tradition. And you're here today. There are a lot of links in the shared handout, so you can start there already, opening these up, Victoria.
Let me take notes about the assistants. So, Ricardo, Manuel, Victoria. The last project was very, I would say, very demanding, maybe compared with the previous one.
Yeah,
So,
I was actually on the forum. I was the TA answering the questions, and I saw it. And there was also some pretty good feedback on this one. That there were some students, for example, that got this cost function wrong in one part of the project, and then they couldn't really continue. And yeah, a thing which is hard for me to teach to, because it's exactly what you learn there in the course, is, for example, using these sparse matrices. I don't know where exactly the challenge was, but like this is super messy. Yeah.
Okay.
But yes, your email sounded like that went okay. Still.
No, it was okay. Well, the case that I mentioned yesterday, it was really it was a really stupid missing. We were copying two extra rows that doesn't supposed to be there. So once he removed the rows, everything went fine. He was able to load successfully the code. So. But the good part was what I mentioned it. He never attended ever any recitation, any office hour.
Yeah.
And he was able to increase his performance, and even committed to attend the next office hours. So he's not sure about the recitation, because probably is the schedule, not for some people it's still early, and if they work and they are not working remotely, like for example in my case,
Yeah, totally.
is difficult. It's hard to commute to home and get in time to take the
Hey,
recitation.
Federico.
Hello.
Yeah, so we're going to start at 35 as always. Today there are more links in the shared handout, so if you want to start with that. And you have a really cool Gantt chart in the background. Federico.
It is on our sheet card.
Sheet card? What does that mean? Hey, Martin.
Of the current master that we are taking.
Oh, wow.
It's good for me to know.
That's really, that's okay. That's then a nice Gantt chart for the master. Hey, Nicolas.
Hello, Andy. How are you?
Yeah, coping. I'm very happy. I actually managed to meet some people here. Europe is very, very crazy. But I actually could share a dinner with a friend. That's like now so special. Sorry, at breakfast. And so I'm now pretty happy. I feel like a normal human being. Hey, Priscilla. We start at 35.
Hi, hello.
Yeah, and whenever you're ready, also when I can see you, then it's then I feel more connected. And I promise, yeah. Today there will be enough check-ins to check that you're all there. And yeah. So how is the situation in Uruguay? I think we never talked about COVID in Uruguay really.
It's increasing. Surprisingly, it wasn't one of the best, the first country that best kept the contained the virus. I would say in an alarming way, because it's a small 3.5 million, and having a rate of over 2,000 cases per day is really alarming. We used to have here, I don't know, 3, 4 maybe, but it's, for some reason, it's increased. It's the summer.
Oh, but that means that you have like, so the number that is used in Europe usually is the number of cases per 100,000. So you're like almost at 100 then.
I would say that we are in red right now. Yeah, it's according to that
No,
scale.
sorry, you're saying 3,000 and 2,000 and it's 3 million. Yeah.
2,000 per day. Yeah, over 3 million is huge.
Okay, so it's like if you say 7 days you're in COVID, so then it's 14,000. So you have like 50. Actually, we're worse in Europe right now than that.
Oh yeah, Europe is a different world. It's more. But here, Uruguay was, I believe, the number one in safety measures and healthy score, but not sure anymore.
Hey Anna, hey
again,
Rodrigo.
in the summer.
Hey Andres.
Hi.
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 Yeah, so one more minute, then we're gonna start. You can, today we have more links in the shared handout, so you can prepare that already. And cool hairs, Anna. I think that is new this week, isn't it? So, welcome to actually workshop 6. Did not change this here. I am now also the TA that answers questions on the forum. So I saw your suffering a bit. That was a tough project. And there was also some feedback. And I couldn't identify you among the ones. But yeah, I hope everything went more or less fine with this project. If you are especially troubled by projects, then also stay longer afterwards, and we can talk there. The next month I'm pretty much into whatever is there, because I'm faced with your questions every day. So I wake up, I do half an hour of this. Today we're moving into the biggest step in machine learning, probably, namely into neural nets, which one can translate with, we do the same thing we did before. We have a loss function and we have a way to calculate gradients, and we do it for functions which have a lot of parameters, and then in a clever way. The structure today will be about the following, because last week I got confused a bit, and I would like you to all catch up on what strategies did you learn in kernels that also help you elsewhere, and also to see where the relations are. I'm going to quickly walk you through the solutions that I wrote to you after last week's meeting to bring you up there to speed. And then we're going to have a bit more relaxed introduction to activation functions and neural nets. Then we're going to do some gradients for neural nets, and then there's a coding exercise. And yeah, in the Matboard, there were no submissions, but I want to show you one thing from last week, and that is this. This is the recitation attendance versus score. And here maybe here any ideas, any comments on when you see this? So just as a machine learning data scientist, what does this tell you when you look at such a regression? Maybe here, let me see. Yeah, Mariana, you don't have your video on. Do you have a comment on what this tells you? Okay. Yeah. So here, one observation one might make, okay, there's also a way to quantify whether this is a better or worse fit, but this seems not to be a good fit. So the predictive performance of this is not very good, but it seems to be positive. And the question is, can you say anything about the effect of requiring attendance at the recitations, so enforcing that very stringently, on performance in this course? So should we enforce attendance by, for example, making you pay if you don't attend? Is that something that you can get out of this plot as a data scientist? Matteo, maybe? You're muted, I think. Okay.
Maybe
Someone
there is some additional factors where we are not considering, or we are not even analyzing in this graph. So
yeah. So it might just be that there's totally no effect of recitations on your learning, And the only thing is that those people that go to recitations just are the group that put in more time in general. Perfect demonstration. It doesn't tell you anything. And the thing that you would then do, and that's something you can read up on, is to look for a so-called instrument, because there could be something which actually should only influence the class performance via the attendance. This could be, for example, like how long do you work in working hours? There you don't expect that your time block that you work in really affects your performance in the course directly, but it will affect your attendance of recitation. Then you can do something that projects the values in your recitation attendance on your how did you work. And you could do something else to get the regression, but there are ways even to fix this. I wanted to show this again to you, to say there's this notion of prediction, which is very much what you're doing in machine learning, but this doesn't tell you really something about what happens if we change something that changes the distribution of our data. And there's one machine learning joke, which is, I have a machine learning joke, but it doesn't work well on new audiences. And here it's like, if we were to change the attendance structure, so whether you can attend or not, then this would be a new data set that you have. But here, so we don't know anything about what recitations do. It seems to be positively correlated. So you, at least that show up, are more likely to go. Then I'm quickly going to, so are there questions right now, things that you would like to raise, other thoughts? Otherwise it feels very frontal. Yeah, also desires what to skip, what not to skip. Otherwise I would do this. Okay.
Do you think it would be possible, because that was a comment last week,
Yes,
to recommend some specific lectures, additional lecture for these the next 2 weeks, that could help to increase the understanding of the topic that we are going to see during the for neural networks, I mean. Not an entire book, but just an extract.
Yeah. So this is something I'm happy to give you. The bit problematic answer, and this is a very bad answer for MITx or edX, is that in this topic, the Coursera courses are just better. The Andrew Ng coverage, so the deeplearning.ai courses, do an amazing job in the beginnings of neural networks. And I just need to try to see, there should be some open version of this. I will send it with the email that I sent you after the course. So after today. But there are really good ones out there. So what were we talking about last week? I was introducing you first this function called softmax, which you also worked with. So here there was this vector wx plus b, and there was some normalization. And you saw it also in the course that you had to implement that. And I was asking you, okay, can you derive the gradient of this softmax? And we can think of this from the view of a neural net as a subroutine. Because we need this derivative in taking derivatives with respect to other things, with respect to weights, for example. And this is a result of the chain rule, that everything in automatic differentiation is in the chain rule. And so then the thing that I gave to you where that I also presented to you was up to one point where I just deferred it, was, okay, how do you take the derivative of this one? And here we were rewriting first the dependence on weight in terms of an auxiliary variable. And you were getting another formulation of the gradient. So far, so looking also at the project that you submitted, does this make sense, what I'm writing here? Maybe I'm seeing in your faces, then again. So, okay, you look still, okay, you don't look totally questioning. Then we were saying, okay, what we do is we take this function, which outputs a vector, and we plug it into some loss function. And we know what we do. So we take, in machine learning, typically, if we can apply stochastic gradient descent, we have a loss function, we plug into the loss function some other functions which have some parameters, and these parameters we then take derivatives with respect to, and then we see where these go. Then I was making some calculations, and here to see the bigger steps are, and you use this also in the project, is you can use one notion of the logarithm, and this is actually the only reason that the logarithm that you're taking the log of in this likelihood. Log makes this problem well trainable, or makes the gradient nice. If you ask yourself, why does the loss have this particular form, it's often to make actually training possible, that your gradients are in some particular form. If you were to put, for example, here, instead of a log, a square deviation of some sort. So you're taking, you would put here like sum of squares, which would be a norm. Then this problem would have a lot of problematic properties. It would be a so-called non-convex optimization problem. You could not easily train. So then going back to this calculation that I wrote, we decomposed the problem into two problems. One was first take a derivative of the individual entry, which is just the class that was predicted under the true outcome. So y is here the predicted label. And then we take, in a second step, the sum of all the possible ones, the normalization in the softmax. And then what we observe is, okay, for the first one, we can use that logarithm and exponential are inverse function of one another, and we arrive at something which is almost identity. For the second part, we copy it over, and we observe then, using some another property of the logarithm, that if we take the derivative of the logarithm of a function, that it's the function over the derivative of the function. We can also observe this. So here, for example, exp of zi is exp of zi is the derivative of this function with respect to zi, because exp of zi is, so exponential takes the function constant, and sum of the zi's is the function itself. So this should be switched. Okay, so up until here, the thing to keep in mind is the math works out because you make the decision to make the math work out. And this is why you see this this special negative log likelihood function a lot. It's just to make the math work out. Then, okay, so up to here, which questions do you have? Okay. You can also tell me that I should just go faster and you want to see neural nets. Okay, seem not super. Mateo, what are your thoughts? Should we go faster? You're muted. Probably your microphone is not working. I'm not hearing you.
If you recall, feed-forward neural networks.
Okay, so I heard Tommy Yakula just talk. That was interesting.
Yeah, sorry. Hey, now you listen to me?
Yes, yes.
Ah, okay.
Yes.
So it was the microphone. Sorry.
Yeah. So yeah.
No, I'm okay
Tommy,
with this. In fact, this part was part of one of the
yes, it
exercises
was.
in the project. It was a bit different, and they calculated the gradient when that was some kind of hard to me.
Yes.
They did it when it's m is equal to j, and with m is different to j, and then they put those things together in a function.
Yeah, and these two cases
where there was p as a probability involved. So it was a bit different how it showed up.
Yeah. What is p in this in what you write here?
P is E over the sum of the exponential over the sum of the exponentials, I guess.
Mm-hmm.
But the thing is that P it was, I don't know, the notation maybe was what was hard in the project, at least to me, because was.
Do you have questions to what you see here?
No,
also.
No, not about this. I understand. Then when I went to the project, it was I tried to do the math of the calculation for the gradient, and it wasn't easy. I came up with something similar to the solution, so I took it as it was good.
Yeah. So here, so here now where you can really say this totally doesn't make sense. I'm happy to spend the time here because the gradient calculation actually today will be very, very similar. Neural nets are not very different. Then we were saying, okay, this gives us this derivative with respect to this auxiliary variable zi. Now, how can we get out of this actually the thing that we care about, namely the gradient with respect to our trainable parameters? And for this, we can use the chain rule again. And the multidimensional chain rule is then, okay, let's sum over all intermediate things. So here the difference ZL, and then let's multiply the two different ones. And there's one we know, and there's one we don't know. But what is this? What is DZI DWIJ? Do you have an idea, Gonzalo? So here, ZI is WX plus B. What is W? Scalar, vector.
Vector.
It's a vector.
Are you sure?
Yes.
It's actually a
X is,
matrix.
X is the vector.
X is a vector, W is a matrix.
Isn't-
And what is the dimension of the W?
It,
It's number of features times number of what is this the supervised learning problem we're solving? We're trying to predict so you were talking about
labels. The number of labels is no the number no the number.
Perfect. So P times number of labels. We are in a multi-class classification problem. So we would like to predict, is it a dog, a cat, a sea fish, a sea star, or so on. This is why W is features times classes. X, what is the dimension of this?
N
The features.
times
Features,
G.
so
Okay.
So P, so this together, so like modulo transposition, now you, after the projects, probably you know transposition, this will give us something in the dimension of number of classes. And what is B?
A scalar. Oh,
No.
no.
Mariana, do you have an idea?
No, sorry, I thought the same, that it was like a scalar, but
It's actually the number of classes. So because this Z, and here maybe Zi is not good to write. Z is really a vector, which we're going to put into this softmax, which is going to give us for all of the classes a number. And a big learning for neural nets is whenever, so there's this thing from Google called TensorFlow. A tensor is a matrix which can have there could be more entries, like R to the N times K times P times N. And this is then called a tensor. And ultimately, if your data becomes more complex, you can have more and more and more of these. And somehow the rules of differentiation don't change. So it could be, for example, x-axis pixel, y-axis pixel, input features, output classes, and so on. And when you learn here, this is totally general. So
Can you see a tensor as a matrix of matrices?
That's a special tensor then. But so I would view it as a list of matrices. Like when you see
Okay.
so you could, for example, so when we write it in NumPy notation, formally, this has a length of the shape of, like it should be, that's the shape. And the shape has length 3. This means it's already not anymore a matrix, because the matrix only would have 2 numbers here. So this corresponds to R to the 1 times 2 times 3. And so we can view it as ultimately a list of matrices. Okay, I would like to move on here.
Andy, have one question. Why is X a vector? Isn't it a matrix? Because you have all the features and you have the all the cases. So so that's set I.
That's right. That's
Okay.
right. Yeah. And
Okay.
ultimately also x would then not be in r to the p, but r to the p times n, and then wx gives you an r to the m times n matrix.
Okay.
That's
Okay.
totally correct. Yes. Okay. Then next we were talking about kernels, and the thing that I tell you, don't think about kernels. The rest of the semester is going to be other machine learning models. Kernels are a thing which really plays out strongly. I said it last time. When you really don't know how to make calculations on things. So you could, for example, say, I want to differentiate some transaction network between people. So you're working for a bank, you have these transactions, you would like to predict which node, so which user has committed fraud. And then you can say, this whole network is X. And you totally don't know how to translate this into numbers. But the pro of using kernels is general data, which is not vectors. In any other application, so if you have this application for your problem, I'm very happy to talk more about the applications there, and there's still some applications, but otherwise, don't worry. Yeah, so the properties that you give are purely abstract properties, especially you don't need to be a vector. Then here, I send you these notes and I wrote out the solutions completely. If you would like to refer, there's some non-examples and some examples, and there is one kernel which is quite famous, which is this RBF, radial basis functions kernel, which has this nice property to essentially classify things that are close to certain points. So to given points on the plane, if you're doing two-dimensional, or just points in higher dimensional space. And then there's some work involved to show that this is a kernel, but ultimately choosing a certain kernel in sklearn, for example, is just you specify which kernel to use. So there would be, for example, kernel equal or metric equal to RBF. Okay, then the part on SGD with kernels. Here, main takeaway that I think I also didn't say, because like it gets very confusing. I got confused with the alpha translation in the dual, but the main point here is machine learning works as soon as we can do stochastic gradient descent. So as soon as we can feed each data point into our problem and we can compute a gradient and we can do some learning rate, we're good. Here you were taking perceptron on the left, and you were taking SGD on the right. The translation is pretty similar, but as soon as we have SGD, we can almost say, okay, work done, I'm going home. And here I'm writing out for you how to translate this kernel matrix, these dual variables, and the labels into things that you care about. And then we were having code, and this code really reflects, okay, you have a certain implementation for SGD, and this implementation you're implementing. This is also the code that I sent you. The main thing here is, as soon as you have SGD, you can write it on your own, but also as soon as you have SGD or you just have a gradient, you can, when you're later on using frameworks, so like TensorFlow or PyTorch, you can let them do this. So there, everything is good. Kernels work because we can translate somehow, we can make it somehow work to look like an SGD. Okay, this is for last week. We're now going into a quick warm-up for neural networks. Before that, so I really like your questions so far. Do you have questions on this last one? So I walked you quickly through the main points. Do you have open things that you're interested in? Okay, let's go into more fun topics. Goals for today. You can write down into a given diagram of a neural net the different expressions that you also saw in the course. So where's the activation function? Where's the output of the activation functions? Where are my weights? What's the output layer? So here you know the notation. The next thing is you will have the images in your head of different activation functions. And we will discuss a bit what is the role of activation functions actually. A third thing is you can derive gradients. So you come to the stage where you can do SGD for a neural net. And this is then almost, when you're at this point, great. Neural network machine learning is solved because we can do stochastic gradient descent. And then I'm going to present you one variant of SGD, which is going to make it perform better, which is called SGD with momentum. And there is a very famous algorithm that you might come across, which is called ADAM, which is exactly based on a refinement of this idea of momentum. But there are certainly, so we can cut off at an earlier point. I'm going to send you off drawing some images on the Jamboards. I give you now 30 seconds to download the files from the shared handout and open your Jamboard from the breakout group that you're in. Can you put in thumbs up if you are already done? Then I see how far you are.
Which file is that we have, the code or the?
So all the links in the shared handout.
All the links.
Yeah. So all the links. Download the. I think it's good if you also download the notes from last week. Then you just have them. But yeah, download the code and open the Jamboard of your breakout group. There should be already something in it. Okay, Anna, you look confused. Maybe I quickly show what I mean. So these links.
It's okay, thank you.
Okay, perfect. You need to reach here. Okay, so in your neural network looks like this. We have an arbitrary number of layers. We have these hidden layers and we have output layers. And there are two ways to represent them. One is the one that you will be working with, and one is the one that you might be thinking about. This is the one you work with. So this is math. And this is figure. And there is a lot of notation. Who of you has seen this already? Can you quickly thumbs up if you have seen this notation already? So you can do it in reality, for example. So who has not seen it? Can you now thumbs up if you have not seen this notation? Okay. So I will walk you through slowly so that you get a bit fresher into this. The ones that have it already, you can think what would actually differ. For example, if we have a different structure of network, maybe you saw already recurrent neural networks or convolutional neural networks. If you haven't, then give me these few minutes. So there is, everything here is vectors. Most of it is vectors. So that could be some r to the number of features vector, which is an input. And here is an a. Some of the people that already know it, why is this called a? What word could this come from? So for example, activation could come from. Then you have the idea of a hidden layer. What we saw so far is not that there are several ones, but for example, last time we were having X and we were transforming it in some way. I will show you in math how this means. And then we were having some function at the end, a softmax function. And we only saw it, we stopped here. Okay, if for you the connection is not yet immediately clear, let me walk through one of the multiplications that we're doing. So there's a number of hidden layers. If you have 0 hidden layers, then we are in last week. So and we have these parameters, and parameters W and B are like the W and B that we saw last week. And W is a matrix again, and B is a vector. Again, it's not a scalar and a vector, but these are matrices and vectors now. And what they do is they take something, the activation in the last thing. So in our case, in the last lecture, it was X, takes it to some Z. Z, we also use the same notation by using this matrix W and this bias vector B. The difference from last week is that we repeat the transformations. And how I think of this, so I also learned this sometime, and I learned it using Coursera back in the day, and I was learning at the same time functional programming. Did any one of you do any functional programming? So Haskell or Scala? Okay, then this doesn't work well, but there is it's almost of a concept of you start out with something, and you can either have the power to write down directly what else you can do with it. That would be a very declarative style. Like in Python, you write down lines, or you say, I'm going to transform one after the other. And maybe in like NumPy, you saw it when you say dot mean, dot value counts, dot summary. It's very powerful to have these transformations one after the other. And the layers in a neural net almost do this. In themselves, they're not that complex, but by concatenating them, by doing one after the other, it gets very powerful. And here it's power through composition. So we are taking functions and apply a function after another. Then there is an activation function. Activation function we can think of as well, something that maps our z's to our next a's. And the activation function will be the second part of the breakout room that I'm going to send you off to. Activation functions, they are now another image works, and this is really an image from neuroscience. An activation function is something like, so you have your neural net in your head, and you have something, a signal that is transmitted. And there's this thing that your neuron can either spike or not. And in the brain, the spiking behavior is really, you need sufficiently much of an impulse reaching a neuron to start pulsing. And different activation functions have different computational properties. And here we are back to the question of why do we use this log from last week? Here's like you choose the activation function which actually makes your algorithms work well. It's totally detached from neuroscience or whatever. It's only chosen to train well. And then there's an output layer, which is, well, you have an output function. What could be this output function, for example? So what was our output function last week? Are you saying something, Ricardo? Someone lights up. So what was the first function that we differentiated? It had some exponentials.
The softmax.
Yes, exactly. Yeah. Softmax is the canonical thing for multiclass. And there are also other ones if you, for example, want to simultaneously classify whether several things are there. So you could, for example, classify it is a fraud and it involves the following type of thing. And then it's not that it needs to be exactly one of them. So now we have figures, and I can tell you that these arrows are somehow related to weights because they map things. Then there here are also some activation functions. And okay, maybe let's write this arrow here. Activation function. Here are activations. And here are, let's call them pre-activations. And these will be the Z's. The first goal of this breakout room is for you to get a bit more used to this. Can you map all the notation that I had here on the last slide? Can you bring that onto this image? Can you draw it? And these are on the Jamboard. Also, you have the link to the slides, I think. Is it correct? Is on the shared handout a link to the slides? Can you quickly nod? Okay, perfect. So you can also open this up. And then there's a second task that I'm going to send you off with. And this is regarding activation functions. And activation functions should behave like if something happens, then it should go up. If nothing happens, then nothing happens. And here's the identity function, for example. What property will the identity function as an activation function have? Will it be very selective regarding what it lets through? Okay, you see. So here the identity that isn't really an activation function, in the sense of that there's no difference between being activated and being not activated. It just leaves everything through. And you can make some fancy theory to say, okay, if the activation function is linear, then actually I can conflate my matrices by just multiplying them together. So the weight matrices. This is like next week, maybe this you see. Then there's a binary function. This binary function has similar properties to the 0-1 loss when we look back much. So 0, 1 law said the problem, it is like, it has a very jumpy derivative, which is almost 0. And here we can say this train's terribly. Because the problem is, if you're on the right side, nothing is going to change. You don't have slope that you can go down to. And there are other ones. The sigmoid you will use, that's a very often used. And they're tanh and rectified linear units, which are used for different goals. Tanh is used if need symmetry. In what way is this? In what way might we care about symmetry? In what way is this function symmetric? So why do we care about any function?
You can move either to the positives or to the negatives, and it will be smooth, a smoother result.
Yeah. Yeah, for this, we would only need smoothness. So this is actually like point symmetric. So it goes up as much as it goes down. The advantage of being symmetric with respect to 0 is that automatically your average activation is somehow 0 and not positive. And the problem with other things, like all of these, might be that they just get, the later you come, the more and more activated you get, because the average activation will be positive. tanh doesn't have this property. Rectified linear unit, and then leaky rectified linear unit, and quasi-rectified linear unit. These variants are all the fancy ones that came up like since 2013. So this is the state of the art. These are functions, and what I would like you is to write and draw, ideally, their derivatives, to think a bit about what properties might they have for training as functions. Okay. Nicholas, can you repeat the two tasks, if you remember?
Yes. First, we have to identify the different things that we have to put here in the picture. Yeah.
All of this?
Yeah. And then write the derivatives and try to plot the derivatives.
Perfect. Okay. Yeah. Thank you. I will give you between, I think 15 minutes, but we will see how fast this goes. This is like, think of it as a warm-up, if you have seen this before. If you haven't, it might be good to just get a bit more images into your head. I'm opening the breakout rooms now. Are there any questions, concerns that you have? Okay, and do use your Jamboards. These things, I think, work less. And you see, I put the 2 images on 2 pages there. Breakout rooms are now open.
Andy, I'm in group number 3. Can you send me?
Yeah, totally.
Thank you.
Ariana, where? Okay.
Number 2, Andy.
Yes. Ricardo? Okay, Ricardo, I just put you in 2. Hugo, where would you like to go? You're muted still.
I believe I was in number 1.
Okay, perfect. Hey. Okay, I think we're all pretty much back. I share here. So there was like some orientation. I quickly go through the Jamboards that you have, because you had different interpretations also of the goals. So here, one which I would call the minimalist. The written asks for Z1, 8L, and F0, and that is great. I exactly identified, and then also written out an expression for this. Then number 3 wrote much more, and you then here conceptual more number 2 and number 5. 5 is still writing. I'm going to write the correct thing. So we can also look for these functions. Okay, this is great. So let's first do the functions. Breakout room 3. Can someone of you quickly present what you found?
Yes, we didn't do the last one. We had no time, but in the first one, the derivative is 1. It's a linear function. In the second one, the derivative is 0 in all the reals. The value, the derivative is 0 if x is lower than 0, and 1 if x is lower than is greater than 0. And the sigmoid is, well, is the derivative is that function we wrote there, and well, the tan h, we didn't do it.
So one very cool property so there are 2 things I want to give you as a hint for things that you do later. The first thing is you can express the derivative of the sigmoid in relation to the sigmoid. So here you see already the denominator seems pretty similar in the 2, and you actually can do this. You can there's a formula which is the derivative of the sigmoid is minus the sigmoid times 1 minus the sigmoid, and that is a very good property of the sigmoid. Now a question to everyone, also the other ones. We have the chain rule. The chain rule multiplies a lot of things. What is going to happen with gradients if we do the chain rule and multiply with the linear activation? So let's say we have very many layers, like 25 layers. That's nothing special. What happens? So we multiply the derivative of the activation function is 1, and then we take the derivative of these weights. What do we see? What do we get? So it would be, so derivative looks like something like whatever derivative of softmax we have, but let's say there is some. Sorry.
It's always the same.
It's actually not always the same. It's like when you go back. So when we want, for example, the weights of the very first, from the 0th to the first layer, then we need to say, okay, 1, which is the derivative of this linear activation functions, times WL times 1 times WL minus 1 times 1 times WL minus 2, all up to down. So ultimately what we see is the matrix multiplication of all these matrices. What is what can happen if we multiply together very many matrices?
If we multiply what?
Very many matrices together.
Maybe they don't have the same dimensions.
They will have the same dimensions because we ensure that in our neural net. So what happens if we multiply very many numbers together?
The numbers increase a lot.
So it could be that some of the numbers are just greater than 1 and we get exponential increase. Or many of them are small,
They go
then
to
we get
zero.
exponential decline. And this is a problem which is called the exploding or vanishing gradients problem, which is what most of this design is for. And the nice thing, if you take the rectified linear unit, what is going to happen regarding to this problem?
The derivative for small numbers will be 0.
It will be exactly 0. So we're not going to vanish because of exponential really small number of multiplication. We will just be exactly 0. So it's not that we do multiplication of very large or very small numbers, because the rectified linear unit kills that.
But for positive numbers, it will be exponential.
For positive numbers, it will be exponential, but this is also what we want. So it should be, so here the idea is if we are like in each layer, it's like the node says, yes, I'm spiking. Yes, I'm spiking. So this is like, it has a lot of activation. And this happens all the times. Then it's like, oh, this needs to pass every layer's test. So the exponential increase in activation is actually desired. If we really have only positives, it should just be that it's completely mapped to 0 for low values, which is not the case for linear. That's very good. And I'm going to write you the other one. No, this is not it. So here, yeah, so we see L is equal to 2 because we have 2 hidden layers. Then we have X, which is equal to A0. Then we have A1. Then we have A2. And we have this A out, which is here just a general one. You might have different notations. Then somehow the activation function is then in here. Then we have weight functions, which are, or weight matrices. So here, the 0th activation, which is the input, is mapped to the first layer with the first weight matrix. Then you have the second weight matrix. And then we have here Z1, which is mapped via F1 to A1, and Z2, and here ZO. And we can go back to the math, and we can take, for example, okay, AL, which is A2. So let me make you here. So AL is equal to A2. We map it via W0 to Z0, Z out. And then Z out is mapped via A out, via F out to A out. When you will implement a small, I think a small like one hidden layer neural net, I think in a project. There, I suspect that there will be a lot of this indexing. But from the abstract point of view, the only thing is, can you write this down properly and can you take gradients? Because then we can use stochastic gradient descent. And sorry, I sound like a bit of a broken record, But for me, this is my perception of machine learning, because I use a lot of automatic differentiation. So all of this gradient business is actually way that you can automate it away later, as soon as you understood it. So we saw these two. Before we go into the second, now bigger breakout room, I just want to show you that what we have done so far actually kind of maps all into the same business. So we can view all of the things that we have done so far, almost, except for perceptron, as neural networks. So if you have, for example, regression, we have an output, which is how many dimensions does a regression output have? Don't be shy. So regression is?
One, it's a value.
Yeah, it's a value. Binary classification, how many dimensions?
It has two values.
Dimensions.
Two.
So typically it's just one.
It's one dimension, yeah.
Because the thing is, what we did was we have this, like we had WTX plus B, which was either positive or negative. And then we would say, okay, classify as 1 if it's positive, classify as 0 if it's negative. It's one dimensional. Then we have multiple classes. And then there's also another case, which is multi-label. This is, you can have several binary ones at the same time. I'm not going to go into this, but this you can also phrase as a neural network problem. And in regression, what we had as activation function was, well, we just take the identity. What was the loss in the regression function, in regression problems as we set it out?
Square distance or something like that.
Say that again, Rodrigo?
Square distance?
Exactly. So here, and we can say 1/2. What is the activation function, for example, for binary classification?
0, 1, or the hinge, one of those.
So that is actually the loss.
Ah, okay, the loss. I was talking about the loss. Sorry.
So here, yes, we can have hinge. How can we view hinge? How did that look again?
It's
max
0 and
1 minus theta.
Yeah, so 1 minus, and
theta,
here, I think it's best to write a y here to have the same notation, but this is the loss. And here do we have an activation function? Well, it's also probably linear. There are also other specifications, but it also works in the same way. And for multi-class classification, what is our activation function and what is our loss? I asked you already for the activation function earlier.
The softmax, or no?
Softmax, exactly. And what was the loss function?
The log.
Yeah, this log thing.
The log thing.
Yeah, I would just write it, say it's the log thing. Yeah. So here, that's yeah, the main point of this is, so let's here say log likelihood. The main observation is all problems we saw almost are neural networks. There's the loss, we have some structure, and they were typically not deep, but they all fit into this class. Okay. Now, I hope you have all, so asked several ones of you to download the slides. Now we're going into gradients of this one. I said last time that we have the most challenging gradients, and I still agree with that. Today we're just having a similar version with differently named things, differently named variables. I'm going to send you to do the first part of it with you, and then going to send you off to write some chain rules out here. So why are we doing this right now? What is the goal to write these gradients? Just to repeat, to check. So why am I bothering you with getting, for example, this gradient? Where do you need this next week? Or whenever the project is due?
Because we have to choose the best weights for each activation. Is that the?
We have to choose the best weights
and the best weights.
And what does that have to do with gradients?
If we use the cases to train the function, we will choose the best weights with the gradient descent.
Yeah, exactly. So what we then write is this is our update, and we need this term. This is why we do gradients all the time. And let's do maybe this one here together. So look at this image. What is, so W is here, and we have here some Z, some F, and the loss as output. What is this?
What do you mean? What is it?
So sorry, what is this in terms of this? So let's say we know, so here we know that somehow there is loss, and into loss I pass, let's go back to the first one. So there's loss of W and the W that we have predicted. W is dependent on the activation function of some Z. Now, I'm saying, okay, we have already given loss up to Z. And now we would like to have loss with respect to Wij. I'm saying you need the chain rule once here. What do you need to do? So I'm telling you that ZIO is W JIO times times AL. Yeah.
So you take the derivative of in W times the derivative that you have.
So W L over WZIO times WZIO WJIO. And what is this?
the derivative of the activation function.
It's A or no? It's C.
So here it is. Yes, it is A. But yeah. So yes, it is A. We just need to know what this is for some, but it's like A JL because it will only be one column. And then there is some other term, which is ZIO. The nice thing is that you can actually go back much further than that. And I would like to try. So, and here maybe the slides are helpful. And I also struggled with this when I learned it. So I label you these ones here now. So you have W1, W2, W3, WO, F1, F2, F3, FO. We have loss. And for now, you can say the biases are optional. But now the question is, if assuming that we know this first loss, and I can tell you even what the term will be, it will be very nice. It is yi hat minus yi. Very nice term. This is just how we chose the loss, this logistic, log likelihood loss. Can you express all of these using the chain rule? And here, maybe, yeah, we can, yeah. Does someone have an idea, for example, for this one then? So which, what do I need to multiply together? And then I send you off to discover it yourself. So this delta W, the derivative by what?
Seed.
So Z out times del Z out del A out times what? Oh, sorry. Actually, this should be A3 because so we are here, then we're moving here. So del A3. What did we apply before?
DW.
There's actually again Z3 because we take the Z via the activation function to the activation. And then we're here. And then we can say del Z3.
Do it backwards.
Exactly. And then the question is, what is this? What is this? What is this? This one here we already know. So node ZO is WO times A3 plus B. So what is this? Okay. Before I lose other people, Edison, you don't have your camera on. Can you quickly check like how it's going for you?
Hi, Andy, but I don't know do it.
Okay. Yeah, for me, it's important. So you will need to do this. And I was explicitly told that taking these derivatives will be on your exam. Otherwise, I wouldn't have done it because I think it's quite cumbersome. And normally I'm not this person, but I'm not writing your exam. So probably not on the midterm, but on the final. The important takeaway here is we apply function after function after function after function. When we take the gradient, we just go backwards. That he completely said correctly. And now the question is like, can we write down the formulas that define each of these points to get what we want? And for example, here,
Yes.
Z0, del Z0, del A3, del ZO, del A3, what is that, given this function here?
WO.
So WO, and this is like a short writing of this, because it's a bit weird to say this derivative is the matrix. In the end, we would like need indices for all of these, which is a bit weird, and we would need to sum over all of the indices. But that you will figure out in the project, in the coding of the project. But ultimately, what you can do is you do matrix multiplications. What is A3 by del A3 del Z3? So A3 is f of Z3. So F3 of Z3. How can we, as what can we view this? Well, F prime of Z3. But the problem is, this also needs to be somehow a matrix. So it's like on the diagonal only to have it. So it's like if you differentiate A3I with respect to Z3J, that's going to be 0. And I would like to send you off for maybe 10 minutes to write out this longer chain of equations and check whether the matrices make sense that you write down. And here, the important thing for activation functions is that this will be a square matrix for activation functions, because so it will be off the diagonal. So because of this one here, it will be 0 wherever you differentiate A3I with respect to some other function. And yeah, as soon as you've written this down, they will be called recursion equations in your next lectures that you do on the course. I think there you're in good shape. I'm going to send you off for a bit. What are concerns right now? So Edison, for example, can you say where we lost you, so that we can maybe pick you up again?
Repeat, please, Andy.
Can you say where we lost you, or where I lost you, so that we can bring you back up? So just to see here, this is, yeah. To frame this is only a tool. Yeah, go ahead.
Where is loss in the map?
Where is low Z?
In the map. I can find the loss in the map. Can I see?
Yes. So the loss comes here right at the end. And the loss is something a bit weird, because the loss you evaluate with respect to y, and we can think of this as yi. So this is really the label of a data point, and the output.
The output of the line.
And what the output that we can actually write down, the output is equal to AO, which is in turn equal to FO of ZO, which is in turn equal to FO of WO of AL plus BL which is in turn equal to FO of WO of FL of ZL plus BL, and then all the way down. It's just a very deep recursive equation. And what I'm asking you here for is to write this down forwards, that's called forward pass, and then to get the gradient of it, which is called backward pass or back propagation. And this is, yeah. So I would like you to, for example, for example, I want you to do this one that I'm coloring in complete blue the next 8 minutes. So as much progress as you can make on this one in a very long list, and then we reconvene, and I'm going to show you some code at the end of this. So it's like going to be a small show at the end. Breakout rooms are open.
Andy, can you put me in group 3? Hey. Okay. So
Yeah, I saw all of you in there. And yeah, so I would like to show you some of the code that we had, because that's like a third thing that I wanted to have you just see. It's another image. The main takeaway for you for the projects that I hope that you get, there is a lot of notation involved, and that might be very intimidating. All of this notation. Ultimately, it has 3 components really. You will have some derivative with respect to the loss. You will have some derivative, which is the activated value with respect to the activator, which will involve some derivative of your activation function, the thing that we computed earlier today. And you will have some activated value from the last layer mapping to the new activating value, which will involve the weight matrix. And these 3 ones you multiply together, one after the other. And after today, you will maybe in the project realize, okay, this is stupid. I don't need a human for this. And actually, what I will try to show you in the last weeks that we have. So I don't know whether we have a session after your final, but there I can show you how you write it in a machine learning framework, where it is really that you never compute gradients. You only write down, this is the function that I first apply, then I apply this, then I apply this, then I apply this, because actually the machine can do for you all the gradients. What you do right now is mainly understand a process that can be automated later. But if you don't understand the process, then you won't be able to debug the code. To conclude today, I want to discuss one image. So this is a simple, so not a simple, so this is a 2-dimensional optimization problem. So you have like 2 weights we can think of, and we would like to minimize the quadratic function, which is minimized at this point 3,3. And these dots show us the different steps of a stochastic gradient descent. What is happening here, or what is the problem?
Can you repeat, please?
Yeah, you were on your phone, but
yeah, that is sorry for that.
No, that's good. That's so it's not good for our discussion because I need to repeat, but otherwise, like, we all have lives and you're all working, and I think it's great that you're doing this. We minimize a 2-dimensional function. X1, X2, we can think of as weights, and we minimizing it like a mean squared error, something. And this shows the training progress of stochastic gradient descent. So you're stepping from one point to another. At this point, 2.5 minus 1.2, you're stepping into the direction of the steepest descent. So the gradient, you're going down, going down, going down, going down, going down. What is going wrong here?
Why is something going wrong?
Say that again?
Why is something going wrong?
It seems to be, it looks a bit inefficient, doesn't it?
Okay.
You couldn't just go straight to the
Okay.
Yeah.
You are thinking about the time you are computing to go to the optimum. Okay.
Yeah, so it seems to be that you're overshooting a bit every time when you're walking in a certain direction. And the problem is that your direction changes every time a lot. It's like you first go almost completely up, next time you go almost completely down. And a concept that comes in here is momentum. Momentum is something that says my update is not learning rate times the gradient, but learning rate times some weighted sum of my last update and the gradient. So I'm almost putting friction here, and we see, okay, this is going to perform very well.
So you want to confirm that the direction is right, something
Exactly.
like that.
You should not always change directions. This is what it says. And so here there was a coding exercise around this. I'm glad that we did the gradient thing because it's directly relevant to your project. But the big thing about machine learning projects, you have about, I would say, you have three things really. So the first thing is you have a certain representation of your features. Whenever you think about text, then you need to think about an embedding. And we were talking, so yeah, embeddings not really came up, but when you looked at PCA, for example, you can think of this as an embedding. The second one is your architecture, which we talked about can be neural network. It can have different activation functions. It can have different rate matrices. And the third is your optimization algorithm. And this optimization algorithm, you can have stochastic gradient descent. You can have stochastic gradient descent with momentum or something fancier like ADAM. As long as the optimization algorithm only needs a gradient, you're good. Okay.
The difference will be just in terms of how efficient it is.
Yes.
The result will be probably the same in terms of the quality of the result, or
this is a great question. The problem actually is that even that might not hold true. It can be that stochastic gradient descent on some examples actually diverges.
Okay.
Because it can be that your learning rate is just too large and you're always overshooting and getting into even stronger gradients and even more overshooting and so on. And their momentum even might not help. That can even be the case. For this, you need some adaptive algorithm, like adaptive gradient descent with momentum, ADAM, which stands for exactly this, which can fix the problem.
Okay.
So it's not only more efficient, but it's also convergent. Okay. To today's goals. How comfortable, so show up or down, are you with writing the output or input expression into a diagram of a neural network? Can you show me like thumbs up, thumbs down? How comfortable do you feel writing down the shapes of different activation functions and their derivatives? How comfortable do you feel deriving the gradient of the loss with respect to weight functions in a neural network? Also like, okay. And so the last one we didn't do. Thank you. This was it for today. I will send you the code for the momentum example. I am not sure whether I will see whether in a later week we have time to do this exercise. I find it very, very nice because this is like the whole sphere of optimization for machine learning. If you have things you want to chat through with me, I'm still here. And if someone is here who can tell me, like today we have had a lot of attrition, how we can have more people stay, I'm also glad. But I think like today was just very tiring with all the notation. But that is it. See you next week.
Bye. Thank you.
Bye, Andy.
Bye, Andy. Thank you.
Bye.
Andy.
Yeah.
One question about the gradient, the last gradient we had to do. You have to write all the expression, or there is a shorter way to do that?
Yes, there is. So what you can realize is that how we define the forward pass. So here, this one defines the forward pass. This is a recursive equation. So we have like ZL somehow depends on.
And
things
it's
with the
always
lower-
it's always the same, that equation in
So
all the
it's
steps.
almost the same. It has different indices. But the nice thing is that a similar recursive equation exists for the gradient. So there, typically you introduce values which are called delta.
Okay.
So you would say delta L minus 1, delta A minus 2. And then you have like delta L minus 1 is equal to derivative of the activation function at L times weight matrix at L times delta L. And this is your recursive equation there. And ultimately, this is what makes it tractable, that you can have that you can actually do the shorthand, because otherwise it would be very messy if you needed to reconstruct this long chain every time. But actually, you can save a lot of memory and computation. That's a great question.
Okay, thank you.
Have a good one.
Bye.
I guess that if you use functional programming, it would be even simpler, right?
Yeah, there's this interesting so I was talking about Scala as a functional programming language, and the interesting thing is it did never really take off for some reason to use functional programming languages in machine learning. And I think that this happened because the people that constructed optimization algorithms hated functional programming. I think it's not really a thing that is very efficient, but I think that just you had a certain community which wrote in declarative languages, particularly in C, and all the optimization packages for smooth functions, which can work with gradients very well, were written in C. And then you had like Python wrapping C, and then Python took off, and then everything came out. But certainly, I think you can write a neural net much cleaner in Haskell. And you see at Facebook, actually, some people do this. So internally. So they're doing it for, I think, actually very socially relevant and very socially relevant. I think their detection of illicit content. So when you write like stuff which brings you into criminal charges.
Shouldn't be there. Criminal.
Yeah.
Okay.
Yeah. So, and I think this is actually written in Haskell. I saw a talk by a Facebook AI researcher. Yeah. Great. Anything?
Bye to you both.
No. Okay, great. Bye.
Bye.
Matthew.
Okay.
Okay, this was definitely much better than previous class. I believe that the reason for start gradually lose people, regardless they might have other commitments, okay, because there is always the chance that you are, but maybe the notation was a bit I don't know how to call it, stressing, tiring, or I don't know what the right term would be.
Yeah.
But this was definitely better than previous.
Yeah. Fortunately, we have some. I think we have one more week with neural nets. It's like then they will see these wow, what's going on? RNNs stand for. Anyway, so the text neural nets, they see that these, and we will have like similar massive notation, but at least they saw it then before.
Okay, I can tell you about how it goes after the office hour this Friday.
Yes.
And in advance. So any feedback or any missing that I might notice during the class, I will pass to you.
That's great. That's very helpful. I will send you the I will send you the slides immediately after this. And yeah, I think that's it. You wanted videos. You wanted videos on neural net.
Yes.
And I think actually I can pull this up now. Let me just see. Because I think actually this is.
Remember what I mentioned about holographic neural networks?
Yes.
I found a couple of papers, but surprisingly, they both refers to this technology like a obscure technology. So as far as I know, in the last 20 years, it never was further developed or adopted.
What I was thinking after this is like, you have sometimes, do you know quaternions?
Sorry, say again?
Quaternions? So it's like a 4-dimensional number system.
No, I'm not familiar with that.
This is even more, you look whether I have it in Spanish. Because it's quite technical. I would even read this in German. Oh, wow. Yeah, here. So this is something which is used in image recognition.
Let me paste in this one.
Do you know these?
Nope, an opening. Just give me a second.
Yeah.
Quaternion. Okay, you mentioned that is an extension similar to complex numbers, but I remember I did literally use complex number over holographic neural networks. But maybe this is it diverged to another kind of technology.
Yeah, I was thinking though. So I'm not sure that complex numbers. So like, where do you really need complex numbers? The advantage of a quaternion is that quaternion multiplication has an interpretation in time. Times are 3 dimensions. This is why it's 4-dimensional. So like in space-time, it can do calculations.
Okay.
And complex numbers cannot, I don't know, like maybe if you're 2-dimensional, but then still not very clear.
Okay, I will give you a reading to this, and
yeah,
but I can share. I can share with you the. Let me see if I can find the link.
Yeah.
No, I don't have the link. I download the document.
Yeah, you can also share it with me on Signal. So I like to learn. Learning is amazing. So
absolutely. Yeah, it's pure curiosity. Why so promising technology was not developed in the last 20 years? That which more or less is the time where I left. But
yeah, but this is like, as I said, Like, why don't we see more functional programming languages? This is purely because humans do it. There is not necessarily a reason that it makes sense.
I use, well, it's not purely functional programming because Dr. Racket is multi-paradigm, but I teach that I have a topic, specific topic in mathematical logic. When I touch the programming in Dr. Racket, which is a direct descendant of Lisp programming. So
nice.
It uses some functional paradigms for it's useful to, for example, to teach you recursion and some other stuff. Is really, but people that when I start teaching that language, most of the students were not interested, and until I put some graphics on it and show them how easy it was to program graphically. Even so, I believe it's more, they go more with the current trend in pro of some other more commercial languages. I don't see in any beyond the academic world that this kind of language is being used in a corporate environment. So maybe that's a reason. So.
Sorry, you're saying Lisp in general?
Yes. No, Lisp.
That is actually not true. There are actually people in, for example, there's one investment firm called Jane Street. They're hiring mostly academics, but they have a large chunk of their code base actually in Lisp.
In Lisp, wow, that's good to know.
And I think it's really like, which people do you get? You can only have a code base in Haskell if most of your people went to super nerdy universities and were nerds in a certain time.
Yeah,
go ahead.
I used to think the same about COBOL until I managed last year a large project for my customer in COBOL. And I discovered that there are IBM released last year a recent version of COBOL. So there are many companies and enterprise worldwide that are still using COBOL, even if you don't find commercially or it's not taught anymore at any university such a language. So the few programmers that are still using COBOL are from an old generation, and they are paid their weight in gold because it's really rare to find that kind of programmers. So, but if you try to even mention COBOL to the new generations, they will say, no, that's a dead language. We don't want to learn that language, and it's not true.
I think COBOL is really dead. But I think also compared to, but I think
about the quantity of line that still exists nowadays in COBOL is amazing.
That's legacy code. That's just people continuing to use code. I think what I like about Lisp, but this is the only way I actually came into Lisp, is metaprogramming. So you're using another language to change the code of a language that you're actually interested in. So you, for example, want to replace things in a C file using Lisp, which is more efficient. So you generate very efficient C code using another very slim, very nice programming language. And this metaprogramming, someone told me about who was a Lisper, and then I saw a bit of Lisp.
Good to know.
But what I was thinking, Hugo, so you were making all of this in like Microsoft Power BI and Excel. You could also do that in Python.
Yes, in fact, there is a connector for using Power BI and Python when you deal with big data. It's more efficient.
I think like even for the the regressions, if you want to
yeah.
learn Python there, you can
Yeah,
totally do this.
Yeah, I didn't make it in Power BI because there is no direct. Well, you have to I believe you have to program. Power BI use DAX as a language for programming. So yeah, it could be maybe it was native there, but I don't know about maybe using Python directly. You're right. I could write it in Python and from Power BI. You can run theoretically any script in Python from within Power BI. So yeah, you were right. I didn't realize about
Yeah,
that.
but I think like, so there also, Power BI is such an immensely widely used system. Like many of the Azure users just breathe on that. I see it also like, yeah, I saw even it here at the European Commission looking into cloud services. Like it's so widespread.
Power BI, with Power BI, you can connect to practically any kind of data source. It could be even some PDF or plain text, any kind of database server, DB2, SQL, MySQL server. So whatever you want is you will find a connector for, and it's really friendly to use. I like it a lot.
Nice. Okay, Hugo, then you sent me just a signal like with things that come up. We will go dig a bit more into neural networks next week. And yeah, I will also send a general, I might actually send you now a feedback. No, I will send a feedback, send out a more thorough feedback form next week.
Okay.
Okay. Have a good rest of the week. I hope you relax a bit.
You too. Thank you, Andy.
Bye.